Thank you for joining us today. My name is Jolie McGrath, the Distribution Coordinator at ThermTest, and I'll be the host for today's webinar. Our topic presented today is the thermal conductivity and resistance of polymers, composites, and layered structures. Before we begin, I'd like to mention our upcoming 3 webinars. All attendees for this webinar will receive an email invitation for our upcoming webinars once the registration has opened. I'll pass this webinar off to Dale.
Thanks, Joe. So, I appreciate everybody taking the time to listen in on the topic. The agenda we're going to talk about is what is thermal resistance and thermal conductivity, a short introduction into specifications of the GHFM, which would be guarded heat flow meter 01 and 02, a short description on how they work, applications for polymers, composites, and layered materials, glossary terms, and a QA period afterwards. So, what is thermal resistance and thermal conductivity? Thermal resistance is the ratio of temperature difference between 2 faces of a material and the rate of heat flow per unit area. How does that translate? Is the higher the thermal resistance, the lower the heat transfer. The lower the resistance, the higher the heat transfer. Or rather, the lower the resistance, the higher the heat transfer. Most appropriate for characterizing non-homogeneous or heterogeneous materials where other modes of heat transfer through a material are present in addition to conduction. So that means any other modes of heat transfer that are in a material, such as radiation convection. This is a good measurement approach. Thermal conductivity refers to the intrinsic ability of a material to transfer or conduct heat. That's the key word. If it is one of the 3 methods of heat transfer, the other 2 being convection and conduction. Thus, the higher the heat transfer, the higher the rate of heat transfer, the lower the conductivity, the lower the rate of heat transfer. This is the most appropriate for characterizing homogeneous materials when the only mode of heat transfer through material is in fact conduction. We'll talk a bit more about that. The GHFM02 is our portable series for following ASTM 1530. There's a new 2019 is the new year for that. A couple keys to pull out of this is it is a simple device for easy room temperature measurement. The new GHFM01, these are the correct specifications for this device. So up to 40 watts per meter Kelvin, -10 to 300 Celsius. So what makes this particular new device special? It combines advanced features of automation of temperature, applied pressure, and thickness sensing. So what does that mean? That means everything is controlled by the computer. The movement of plate is electric. The sensing of thickness is through digital encoder, which has a high accuracy. It also, you can set the applied pressure. So essentially you could set up an experiment to automate different temperature steps, different thickness steps, and different applied pressure. So we've really put a lot of development into automating much of those experimental parameters. How it works. So the essence of a guarded heat flow meter is in the stack. Your sample would fit between 2 plates that would encompass the full stack. The testing stack is made up of a heater or an upper plate with integrated temperature sensor and heat sink. The lower plate has also 2 integrated temperature sensors, 1 on each side. Your sample is introduced to this. Those 2 plates come together. Once steady state temperature across the sample is achieved, we can use, we would record some temperatures, use a Fourier law equation, and from that we can get a thermal resistance. This is a calibrated device. We do, the ASTM standard and this method requires a contact agent between the plates and the sample, and we would calibrate those away. That can be done by the user and or the factory, but the effects of that contact added agent is calibrated away. So once we calibrate that away, we're looking at the thermal resistance of the sample itself. Once we know thickness, the thermal conductivity is also reported. So this is a short video that would just show a typical sample setup for our GHFM02. Again, this is a room temperature device. The plates can go higher and lower than the mean temperature of near room temperature. So we call it a 20 to 30 degrees Celsius room temperature device. The plates above and below would go 10 degrees above and 10 degrees below. We basically call the mean temperature a room temperature device. So we're applying paste to the sample and fitting it between the two plates and bringing it together. So once we click the start test, we're waiting for steady state conditions to be met, and then the thermal resistance and thermal conductivity is recorded and conductivity calculated. Okay, so this is the meat of the presentation. Anisotropy in polymers and composites. So anytime that there's a use of a filler for mechanical or enhancement of conductivity reasons, or processes such as 3D printed, or direction of extrusion, so extrusion of a rod or plate will create anisotropy. The degree of anisotropy could be small or large, of course. Fillers or particles are used to increase or decrease conductivity. Those fillers can vary by shape, type, and density. That leads into how does this affect measurements? So contact transient methods, that's what we classify all transient methods that come in contact with the material, and the typical description would be, an electrically conductive sensor of some kind, electrically insulated from the sample. A transient from the sensor is applied to the sample, and simultaneously we're reading temperature to record a temperature rise versus time. So if any anisotropy is introduced through the previous mentioned processes or fillers, are highly organized in repeating through the thickness, there are a number of transient methods that will give satisfactory results. If the thermal conductivity of the fillers or particles are close to the conductivity of the matrix, particle shunting is minimal. We'll talk more about what that means, but essentially the images below, that is an isotropic homogeneous material that a sensor is applying heat, rather supplying heat, and the heat is diffusing. We would record transient versus time raw data, and the calculation model for that would hold true because we are in fact penetrating all directions the same. So what about if those two cases aren't met? So what if anisotropy is disorganized and non-repeating? So disorganized doesn't necessarily have to be through the thickness, that can be any direction, but if it's in addition, non-repeating through the thickness, the anisotropic calculations are not accurate. The more they're disorganized and non-repeating, the more inaccurate the transient calculations will be. And that's because those calculations rely on a specific shape, a well-defined shape of penetration, and disorganized and non-repeating will not satisfy that. If fillers and particles are significantly different in conductivity compared to the matrix, particle shunting is a significant source of error, causing internal temperature gradients. So what does that mean? During a transient, which is typically in the seconds, 1 through dozens of seconds, this sensitivity can overestimate the conductivity and cause distortions in the shape of the calculation model. So whether it's 1D, 2D, or 3D, and it doesn't matter what sensor shape it is, that can have an impact. So what does that mean? What is this shunting? So if you look at these examples we have that are just images, you see we've added particles to a matrix. In this case, the particles are actually insulated in nature. The matrix would represent a more conductive matrix than the fillers themselves. Now, somebody would have introduced these particles to reduce the overall conductivity. Now, in the measurement of these with a transient method, what is actually happening is the heat from the sensor through a transient is shunting around the matrix and almost ignoring the effects. There would be some small effect, but almost ignoring the effects of the low conductivity particle or filler. So this could be a glass sphere in a polyurethane foam. This is a documented case actually. And if you were to compare transient results on that type of sample, so glass-filled ball inside a polyurethane foam. They're trying to bring the overall conductivity down. With a transient, it can be quite sensitive to this. So you're creating the second error would be a distortion in the calculation model, because now you don't have an isotropic sample, and now you're applying a three-dimensional average to that. 1D or 3D or 2D, the same setting would be there. So the opposite is true, that if those particles were conductive and the matrix was more insulative, like a polymer and a metal filler, you would actually be shunting through the particle. So the shape of this might look a little different, but you would be overestimating in both cases compared to full thermal resistance, which is what we'll talk about next. So if you're measuring this same type of sample with a steady state approach, and the anisotropy is disorganized, non-repeating, it could also be organized and repeating, of course, the measurement of thermal resistance is recommended. Why? The guarding will ensure against any lateral heat loss, so that's eliminated in that setup. Full thickness, this is the more important part. Full thickness is represented in a one-dimensional thermal resistance conductivity. So how does this measurement how is it improved over training for these extreme cases where the particles are very different in conductivity in the matrix? Is that the temperature gradients are evolving and mature. So the effects of those particle shuntings are negligible. The GHFM measurement typically takes 30 minutes, maybe 20 minutes, 30 minutes to achieve steady state conditions, which allows these temperature gradients to mature, ensuring that the overall conductivity is actually measured. And you're measuring that from plate to plate, from side to side. So that's an important component of why steady state. It may not be quote, quote, fast, but for true value, when you consider this source of error, it is well worth the time when you're looking for accurate results. This is a well-published phenomenon. There might not be a lot of discussion on how it and why it happens, but you can get a bias anywhere from 10 to 40% between transient and steady states. The aforementioned example I had, which was glass-filled spheres in a polyurethane, there's about a 15% bias between transient and steady state. In that example, a third decimal place in conductivity difference is extremely important in the application of that material. So they really do need true conductivity. Anisotropy in layered materials, it has some similarities, but some also slight differences. Those layers can be high or low conductivity, or a mixture of both. Thicknesses can vary, of course. So this is interesting. The anisotropy can be more pronounced when measuring with a transient method. So what does that mean? The contact resistance out of plane or through the layers is in series. The contact resistance between layers in plane is in parallel. So you have reduced resistance. So if you have no guarding and you're passing heat from one side of that sample, and you have no guarding to limit the lateral heat loss, the resistance in parallel is a reduced contact resistance as compared to series. You actually have a greater potential for overestimation in one direction versus the other. So it can be difficult to define how much of your heat is actually penetrating through the thickness, depending on how different the conductivity between the layers is. So it's similar to particles, but more uniform in that you have layers of a defined thickness. So if the layers are repeating, individual layers are not too different in conductivity. Various methods can give pretty decent results. The layers should not be too thick. Why? Is because you lose sensitivity. That's an important component. With high degree of anisotropy, directional heat loss is not well defined, meaning you'll have data, but you won't be able to tell with high accuracy how much your heat is lost radially or penetrate radially or in plane versus through the thickness. Short transient test times can be more sensitive to the contact resistance between the layers. You'll see that because again, it's through a transient, so that impact is more dramatic. Then measuring steady state, where the full thickness is represented, one-dimensional thermal conductivity, the gradients caused by the individual layers. And again, these are individual layers that's intrinsic to the material. There's no paste or anything. This would be a structure that's defined as a layered composite. So those are mature and included in the thermal resistance measurement. That would be the end of the presentation, but there's a couple things to pull out here. Transient and steady state, really steady state defined as properties do not change, the system has evolved, meaning the properties are stable. And in transient, short times meaning changing with time. So how does the conductivity from each of these get applied in application? So if your steady state use of a material, rather, if the material is going to be used in a steady state method, the accurate conductivity in its true format being defined as steady state. Now, again, if you have homogeneous and isotropic, it'll be the same number. But if you have a composite, you want to make sure that your data from whichever method is valid for its steady state application. Now, if it's only used in a transient or used in both, that could be an interesting sensitivity, that the transient will sense the use of those materials in a transient way. And then if there's a secondary application of steady state, both could be interesting. Now, in a transient method, one of the strategies to reduce some of this effect is bigger sensors and long test times. That is certainly a capability, but it's still proportional. That shunting that's referred to in the last point, that shunting is still proportional. So the larger sensor, larger sample, if the particles are uniformly distributed, you're still going to see that effect, which will have some bias compared to steady state. And I think that's it.
Thank you, Dale. So we'll go ahead and read some questions that were submitted during the webinar. For those who haven't submitted any questions, we're now accepting them. So please be sure to type your questions into the question box in your control panel. It's the box on the right-hand side. Questions that are not answered during the remaining time will be answered in email for Thursday, September 17th, along with the link to the webinar recording. So I think we're just going to wait a few minutes for people to type in their questions, and then Dale will begin answering.
Um, 12 micron thickness sample can be measured. That's a fairly thin sample for the guarded heat flow meter. There is a strategy to measuring with different amounts of layers, measuring the thickness. You can get the effects of contact resistance. Again, because you have series of resistance in series, there is that is described in the ASTM that you can measure different layers and back out the effects of contact resistance by having different thicknesses and known number of layers. So it is possible. There are alternate, that's one thing at ThermTest, we have a number of methods at our disposal to assist. So there certainly are methods that would measure the intrinsic properties with no layering at all. We certainly can demonstrate those to you. About carbon foam. So sure, it really falls into that carbon being, I guess, a conductive matrix with pores. So that one of the examples I gave fits for this, which is you have if you want to think of it, an insulative component, and the heat is really going to shunt around for transient methods. So you really want to measure that through resistance. If your sample size fits this method, so the sample size for a guarded heat flow meter is 2-inch diameter, this would be an extremely valid, and what this method was designed for is your type of sample. So it could be done. Regarding high temperature, yes, the high temperature for our GHFM 01 is 300 degrees. I don't know if that matches your high temperature requirements, but that is the maximum temperature range for this device. Again, that's a 300 degrees upper plate temperature. So if you have a 20-degree delta, the max mean temperature based off a 20-degree delta is in fact 290. One side would be 300, the other side would be 280 Celsius. Any other questions? So there's a few more. So here's the question. So is it then possible to characterize anisotropy of a material in the sense that depending on the thickness of the material and depending on the XY heat spread characteristics, this will give you certain distribution? Well, when it really depends on how you cut your sample and how well you know the orientation of your material, whether it be fibers or particles or layers. If you know the orientation of your material, whether or from a process, you definitely would understand which direction you're measuring when you set the sample up. So you're measuring through the thickness in that experiment. So for a layered material, yes. For a layered material, for whatever that might be, anything between the plates, you're measuring through it. So you have that orientation. If you want to switch the orientation and you can prepare a sample 90 degrees to that, you could have the other direction. So that does require preparation of two samples, but that's still, if you look at what we've been talking about for true results, that probably is the best for these complicated materials. It probably is the best way to describe, or rather to measure them. 1,000 degrees, no. That this again is capped out at 300 Celsius. There are other steady state methods that are for higher temperatures, and that would be ASTM 1225. That's a longitudinal guarded heat flow meter. We have one in our lab, but of course we don't make one, but we like to share that information. So there are other methods, but this particular method can't go to 1,000 degrees. What is the samples? Another question, what is the sample size? So the defined must-have sample size is 2 inches diameter. So there's no, now there can be a little bit of a plus minus there, but the sample really should be 2-inch diameter. The thickness can vary up to 1 inch thick. So that's the opening size of both models of the GHFM is 1 inch thick. So that's your sample dimensions and range. So really the variable component is the thickness. 90-degree rotation would require super thick sample. Again, it depends on the shape of your sample. The 90-degree rotation could be, again, 2-inch diameter by your defined thickness up to 1 inch thick. So it doesn't have to be 1 inch thick. So if you can cut from your sample to achieve that, or 3D print, whatever it be, it is possible. For samples like bricks, can we test conductivity? Of course. The plates should be should come together on the sample in an intimate manner. There's a contact agent to fill in any imperfections, but certainly bricks, concrete are a great sample for this particular method. I want to test thermal pad with 0.3 to 10 millimeters. Of course, this device is well designed for thermal interface material. ASTM E1530 is very typically used. The 01, the one that I've mentioned previously, that has some interesting capabilities that no other maker has, and that's the ability to schedule pressure, temperature, and or schedule thickness change. So you could actually set up an experiment to mimic an application of a thermal interface material between a chip lid and a heat sink or something like this. That's a pretty important advancement we've made in this method, to be able to do that all automatically within one schedule. It's the same question, the micron thick. So again, it's the ability to measure one single layer of a material in the micron level is not possible with this method. Again, there is a strategy to layer several pieces of thin materials to multiple defined thicknesses and measure the resistance of those, and you can get the relationship of conductivity minus the contact resistance. That's described in the standard. Again, there are other ways of measuring the intrinsic of a sample that thick. One of them would be the SSTR fiber optic system we have. We can certainly send a link to that when we send out the webinar. That's for measuring the intrinsic. It's a thermal optical method. That would be a more elegant way. But again, if you have a limited budget and you're looking to make some measurements and are okay preparing several thicknesses, there's a possibility you could do it this method with the multiple thickness approach. That's the way of backing out the effects of contact resistance. and it would mean you still have to count for anisotropy in the other direction. If this method is guarded. So if you're not interested in measuring the anisotropy in the other direction, the effects of lateral heat loss is guarded. So how that works is with a 20-degree delta, there's actually a guard brought down around the sample at the same mean temperature that you're measuring at. So that limits the effects of, radial heat loss. So you're really looking at through, that orientates the heat flow through the thickness. So you really do have a defined one directional heat flow. So if you don't care about the other direction, you can test your materials in confidence that you don't have heat loss radially. There's lots of papers describing that and proof experimentally. If you're interested in measuring the other directions, you could prepare a sample and measure that from another direction. Can we, another sample is, can we measure a rectangular sample? No. This requires 2-inch diameter only, and the thickness can vary. So if you want to measure a rectangle sample and you are you want to make good measurements, you really have to consider what the trade-off is. Again, if your sample has very conductive fillers and a low conductivity matrix and they're not well defined, you might want to consider what's the trade-off in that source of error versus true measurements. If your fillers are close to the conductivity matrix and your anisotropy is well defined, you could use a transient method. That certainly could test a rectangular sample. Any other questions? What ASTM? Yeah, so the ASTM that covers this method is ASTM E1530, 19 would be the most recent year of publication. This method has been around for, the guarded heat flow meter has been around for decades. The original ASTM for this method goes back to the 90s. Okay, so there's a theme here. Which method is suitable for thin films? I'll answer that again. Again, you can measure thin films with this. Thin films can be defined by, it might be different. My thin film might be different than yours, but you can measure thin films in general, which is described in the standard, by doing different layers. So one layer of thin film of 0.1 millimeter would be too thin to detect. This method would be invisible to it. But you can add multiple layers and measure the resistance across, let's say, 5 layers, measure the resistance across 10 layers, across 15 layers, and get an effect of the conductivity with contact resistance. And you can back out a pretty good conductivity from that. So that is a well-defined and described approach of using this method to test thin films. Again, there are other methods that might be better suited that we're certainly willing to talk to you if you reach out to us. Anything else? Okay. Thanks everybody for joining us. It was an interesting topic, and I think you'll see an email with this recording at some point in the near future. Okay, thanks very much.